Let us continue our discussion of computer organization subject, Unit 5, which is performing arithmetic. In the previous video, we had seen unsigned multiplication example. So, this was that example for unsigned multiplication. These are the two numbers which are M stands for multiplicand, Q stands for multiplier. So M multiplied by Q is equal to P. C and A are used in the algorithm. C value is 0 while A value is 0, 0, 0, 0. The number of bits used to represent these numbers are 4. So the value of n is 4. So the number of iterations will also be 4. Now here the conditions being specified are we have to look at Q naught value. So if the Q naught value is 0, we have to perform right shift. If the Q naught value is 1, we have to perform A is equal to A plus Q and A is equal to A plus M and then shift. So this is our example. Q, the value of Q is 6. So 6 binary representation is 0, 0, 1, 1, 0. So we have kept this in order C, A and Q. Then we are looking at the Q naught value. This is Q0 or Q naught is 0. If it is 0, then we are shifting it to right. So the rightmost bit is 0, which will be vanishing. So we have 0, 0, 0, 0, 0, 0, 1, 1. Now let us look at the Q0th bit which is 1. If the Q0th bit is 1, then we'll be performing A is equal to A plus M. Here the value of M is 7 and 7 binary equivalent is 0, 1, 1, 1. So this is A is equal to A plus M we have performed. Then again we are shifting to the right. This becomes the second step. So once we shift it to right, the new number is this 0, 0, 1, 1, 1, 0, 0, 1. Then again if you look at the rightmost bit is 1. Okay. So this way we have to just check the conditions. Q0 is 0 or 1. If it is 0, shift right. If it is 1, A plus M, then shift. This was what we had seen. Ultimately, after 4 iterations, whatever number we get, that we are converting it into a decimal equivalent, which is 42. Same thing happened with the second number. 13 multiplied by 9 is 117. Here 13 is M, 9 is Q, M stands for multiplicand, Q stands for multiplier, and P stands for product. The value of M, binary equivalent of M, which is 13, is 1101. So Q is 9, 9 is the binary equivalent of 9 is 1001. Same thing, the rightmost bit is 1. So performing A plus M and shift R as one step. So A plus M will be 1101 because M value is 1101. Then you are going to shift it to right, so the rightmost one will be vanishing. So now this number, if you look at the rightmost bit, it is 0, so shift it to right. Again it is 0, shift it to right, so 3 steps are performed. Now it is 1, perform A plus M and shift it to right. So A plus M is this 1110 and this 1011 is kept as it is. Then shifting it to right will yield this at the fourth iteration, this number 01110101, whose decimal conversion we are doing binary to decimal, and we are getting 117. This was which we have already covered. Now we are going to look at Booth algorithm from unit 5. Now, Booth algorithm from unit 5 will be focusing on signed multiplication. So same bits are there, A is there, Q is there, M is there, and the size of A, Q, M is we know is n bits. How many number of our bits are used to represent the numbers? Let us say 4. In our example, we have taken 4. So the value of n is 4. As the value of n is 4, the number of iterations will be 4. So Q1 is a single digit. One bit is required to represent. Q1 value is, I'll call it as Q minus 1. The value is 0. So now if you compare Booth with the previous algorithm, in Booth algorithm we have to look at two bits, q zeroth bit and q minus 1 bit. If the combination is 0 0 or 1 1, then we have to perform the right shift, which is circular. If the combination is 1 0, then we have to perform a is equal to a minus m and right shift. If the combination is 0 1, then we have to perform a is equal to a plus m and then right shift. This will be repeated for n number of times, is 4 number of times. Let us take the first example. 5 multiplied by 4 is equal to 20. So 5 binary equivalent is 0 1 0 1. 4 binary equivalent is 0 1 0 0. Then 20 is the product. This 5 is multiplier, this q is multiplicand. Okay. So m, we have to beforehand only convert this m into minus m for further requirement. So minus m will be 2's complement of m. So the value of m is 0 1 0 1. So 2's complement of m will be 1 0 1 1. 2's complement of m will be 1 0 1 1. Same thing here. Now a is 0 0 0 0. q is q is 0 1 0 0 and q minus 1 is 0. So we have to look at the two combination, q zeroth bit and q minus 1 bit. So this, if it is 0 0, shift it to right. Now it is circular. Now it is circular. Okay. So again, if it is 1 0, if it is 1 0, then you have to perform what? You have to perform a minus m and then right shift. So like that you have to go on performing till 4 iterations, and you will be getting this number whose decimal conversion you will be doing. So this becomes 20. Same thing with the signed number. Let us say 5 multiplied by minus 4 equal to 20. So here what we have to do is this minus 4 is minus q. So minus q's uh, 2's complement number we have to take. So as q is 0 1 0 0, minus q will be 2's complement of q, that will be 1 1 0 0. Same steps are there. Look at the q 0th bit and q first minus 1 bit. So if it is 0 0, right shift. If it is 1 0 a minus m, if it is 0 1 a plus m. Same steps are there, but it is circular shift. The rightmost bit will not vanish. So at the end, whatever at the fourth iteration the number we get, you will be converting that number into its decimal equivalent. So as you can see here, after fourth iteration we have got this 1 1 1 0 1 1 0 0. So this number uh, will be minus 20. But how it is minus 20, I just need to confirm from the previous example. In the previous example I got this 20. So 20 is this 0 0 0 1 0 1 0 0. How this 20 is calculated? This is 4 and this is 16. So 4 plus 16 is 20. Now this is plus 20, positive 20. So the negative 20 will be 2's complement of this. So let us take 2's complement of this. If we take 2's complements of this, it is coming to be 1 1 1 0 1 1 0 0. So that becomes our resultant. So with this we have stop discussing Booth's algorithm.